So today what we're going to do is, so first of all I'm going to very briefly review what we talked about last time. We're going to complete the argument by looking at the boundary conditions, symmetry-twisted boundary conditions of these models. Show that for two dual models, these boundary conditions, or the sectors rather, which is the combination of the boundary conditions and the charge sectors, are in one-to-one correspondence, and this will allow us then to have isometries relating the spectra of dual Hamiltonians. So this will be the first part, and then in the second part I will do an example. So this Kennedy-Taseki duality I mentioned at the very beginning, using our tools. And I will use this example to motivate some applications of this framework. Okay, so what we saw last week, we saw this generalization of the anionic chain construction. And so graphically, how it looks, so we had our sort of operators, which only depend on objects and morphism in the input, the starting point, which is our fusion category C, right? And what we did is that we considered different types or different Hilbert spaces using some extra information, which was a choice of a module category M. So this was a C module category. And what we saw is that when you, for a given M, the symmetry of the resulting model, so the topological lines that are going to compute with the Hamiltonians, these were valued in what I call the Morita dual of C with respect to M. And so I mentioned in particular, so this Morita duality or Morita equivalence is a statement that for any possible indecomposable module category you make you make here, or all possible choices of indecomposable module category you make, the resulting symmetries, there is a sense in which they are equivalent. We're going to see that a bit more today. But what it means is that morally they contain the same amount of information. So for instance, one example we saw is that if you start from a theory that has an ordinary symmetry G, which is encoded in this category vec G, we saw that the dual with respect to vec, which is this category where basically you forget the group, then the dual was a category of representations of the group. So physically it's a statement that if you start with a theory with an ordinary symmetry and you gauge the whole symmetry, then you have a new theory whose symmetry is a rep G symmetry. And this equivalence here translates the fact that essentially if you know the reducible representations of a group, you can reconstruct the group from that. So there is as much information in this category as you have in the original one. So this Morita equivalence is essentially a generalization of this idea. Okay, so let's talk about the boundary conditions now. So far in terms of boundary conditions, we've only seen in the case of the Ising model, it's called periodic and antiperiodic boundary conditions, which were encoded by it was a deformation of the Hamiltonian, and there was one term in the Hamiltonian that would acquire a minus sign when we had antiperiodic boundary condition. So now I'm going to present like a more, I would say, systematic way of thinking of these boundary conditions, and I will explain then how we recover the case, for instance, of the antiperiodic boundary condition of Ising. So the idea. So I'm going to call this symmetry-twisted boundary conditions, and I will justify the name a posteriori. So what we are asking is that we have our, let's say, our chain, which ends with some degree of freedom here, mn plus 1. And so the chain is, let's say, periodic like this, but we want to decide how we're going to essentially identify the degree of freedom at site n plus 1 and the degree of freedom at site 1. So choosing a boundary condition is basically choosing a way of identifying, of closing this, of identifying these two. So the first thing, so let me just write this. So boundary condition, loosely speaking, a closed boundary condition is a way to identify the degree of freedom at site n+1, n+1 and n1, sorry. Okay. So what we are asking for here is essentially a map, which I'm going to write F, from module degrees of freedom, so module category to itself, which essentially is a map from degrees of freedom to degrees of freedom. And say that the degree of freedom, so we could, periodic boundary condition would just amount to saying that mn+1 is identified with m1, but we could do this in a twisted way, which would amount to saying that maybe the degree of freedom n+1, we first apply some operation to it. So for instance, it could be flipping it or something. An interperiodic boundary condition would amount to flipping before identifying, and then identifying. With the extra caveat that these degrees of freedom, even if I start from simple objects in my category, the image of this operation might not be a simple object. So I cannot really ask for, strictly speaking, identifying them, but I can ask for the next best thing, which is to say that this one is a simple object which appears in the decomposition of this object in the category. So it can be quite exotic. I mean, like, so in some cases it's very simple. It just boils down to saying we just identify them, or we identify them after flipping them or something. But let's say if these are labeled by irreducible representations, it's a bit more exotic. And what we can say is that okay, you take your irreducible representation, you map it to another representation, which may not be irreducible anymore. So you decompose into irreducible representation, and this one, you impose that this one has to appear in this decomposition. So in general, so with this definition, in general, the Hilbert space actually has sort of one extra degree of freedom. We have well, I don't really want to say n+1 degrees of freedom, but we have degrees of freedom at n+1 site. So by that, what I mean is that in the simple case where we are really just identifying this, then effectively, well, this only count as one degree of freedom, right? mn+1 and m1, they reduce to 1 degree of freedom. But when we have this more complicated type of constraints, we really have 2 independent degrees of freedom. There is additional freedom there.
I just want to make sure I understand. Mm-hmm. So you are considering all states in the regional Hilbert space with a constraint which you wrote there.
Yeah. So effectively what
you're imposing this f of the fact that f of mn+1 should contain m1, you impose it as a constraint on the Hilbert space.
Yeah, so graphically what I'm saying is that I have an f over here. I'm choosing this f, okay? And for my Hilbert space to be, for this to describe a non-zero state, I need this Ham space to be non-trivial, which means that this object must appear in the decomposition, in the result of the action of this on this. So in some cases, let's say if everything is group, these are all group variables, well then making the choice of boundary condition here, I'm going to do this example, but making the choice here, given the degree of freedom there, it fully constrains this one, right? So then it's just, we are just saying we are identifying them after multiplying by a group element in that case. I will do an example in a second, maybe it would be clearer. So that's the first thing. We just asked, this is just about closing the chain, essentially. And then we have another requirement is that, so this, I can think of this as inserting a defect, essentially. And we require, so the second part is that we require this defect to be topological, which very concretely in that case means that we should be able to move this defect around here I decided to put it between these two sides, I should be able to move it around, right? Another way to put it is that if you put the boundary condition in a specific position, and then you have the same Hamiltonian, but with the boundary condition it's somewhere else, there should be some unitary that relates the two Hamiltonian. So this, in our case, since we have, remember, we have this action here of the objects in the original category, this will require that we want to be able to move this around, which will, in a way that is very similar to the way we define symmetries, require that the action of this F commutes with the action of these objects in the category. So we require this, requires some isomorphisms of this form, which I wrote down last week already in the context of the symmetries. Okay, so this tells us that we have it's a well-defined.
Wasn't it? It was our definition of the dual, no? That we have this omega.
Yeah. So this is not a coincidence, because this is why I'm calling them symmetry-twisted boundary conditions, because what I'm trying to motivate here is that boundary conditions, this type of boundary conditions, precisely amount to having a symmetry operators, but instead of acting on the whole Hilbert space, it acts at a given point, but then it extends in the time direction. So usually we make the distinction between operator and defect. In that case, the symmetry operator is really what acts on the Hilbert space. The symmetry defect is what gives you these twisted Hilbert spaces, like this. So this is not a coincidence if it boils down to the same thing. Yeah.
But this is sort of a statement of F duality.
A state. Yeah. So in the Lagrangian picture, then this plays exactly the same role, right? If you imagine, then you're in the torus, then this just amounts to having one operator, one defect along one contractible cycle and the other one along the non-contractible cycle. But they play a not quite symmetric role here in the Hamiltonian picture. Yeah. Okay, and then so the effect of this boundary condition on the Hamiltonian. Well, this is using the usual graphical calculus we've been using. So we have something that looks like this now. Okay, so graphically, I remember that this statement means that we have a way of moving this line past this other one, right? So the action of the Hamiltonian using this graphical calculus, how it looks like, where as before, we're going to start by using it's called F move to get something that looks like this. Okay, so far we don't see the influence of the defect yet. The influence shows up here when we have to use one of these omegas to move one of the lines past the defect. Okay, and then we finish the same way we usually do in order to go back to the original configuration. So here I'm doing two steps. Usually before I decompose this into first we get this bubble and then we pop the bubble. So it means that your Hamiltonian, the term that acts across this defect will be modified by the presence of this defect. Sometimes in a way, sometimes it will just be a phase, right? You will just pick up a sign, and sometimes it will be more drastic, especially in the case where we really have two independent degrees of freedom there, and then we can get some fairly complicated boundary conditions. So let me just do one quick example, for instance. So using the duality here between vec_g and rep_g, we briefly talked about this last time. So let's say I'm starting from. So I'm choosing I'm choosing vec_g as my starting point, and I'm choosing the module to be vec, and then we already established that then the symmetry will be labeled by rep_g. So same story for the twisted boundary conditions. So we have boundary conditions here. Well, actually, let me do it the other way. I'm going to start from rep_g rather. and then choose vec. And so here the symmetry will be given by vec G. So this was the case, for instance, for when we got the Heisenberg XXZ model, which was rep D6 as a starting point, which was vec as a module, and then we got the Heisenberg model, which had in particular a D6 symmetry, so vec D6. So then how does it look like? So this operation here, the omega, so I think I wrote this down briefly last time, but so graphically, this action of moving the defect past the lines labeled by objects in C, it looks like this. So I have an E-rep rho. I have a group element G. So group element here is the twist, and in that case, it's simply given by the Wigner matrices, the operation of pulling through essentially the defect. Like this. Okay. So in the case of the Heisenberg model, for instance, so for XXZ, the XXZ model we did, what this gives rise to are identifications between spin degrees of freedom, where we have the one at site 3 plus 1/2, which is twisted by the action of the two-dimensional representation. So if you remember, when we get the XXZ model, we chose this object over here to be labeled by the two-dimensional representations. And so we get something. We recover the usual boundary conditions, actually, of the usual boundary conditions of the XXZ model, something that looks like that. So the spin operators, this can be X, Y, or Z. They are twisted by the action of the two-dimensional representation. So now let me relate this. So this is the way we think about boundary conditions in general. Now in some cases, so there are basically two ways of thinking of boundary conditions. Either you modify the Hilbert space like we are doing here, or you work on a fixed Hilbert space, but then you modify the Hamiltonian. So the way I did it in the first lecture, I didn't want to use this picture yet, so what we were doing is that we define antiperiodic condition by just modifying the Hamiltonian, but we're working on the Hilbert space. So now let me explain how these two pictures are related to each other. So let me do going back to the transverse Fuzzy model. Okay, so there, the Hilbert space, the way it looks like. Something like this. Okay, and so the way, remember that the way we've been thinking about it is that I would always kind of fix the degrees of freedom horizontally, and then this will fix the ones that are there. So this is the degree of freedom I set Gn plus 1. Here I have G1, G2. And so as I said, there are constraints. So for instance, the one over here has to be the sum of G1 plus G2. And this one has to be the sum of Gn plus Gn plus
1. Minus G1.
Well, it's Z2 there, here. Yeah, so like Z2. But yes, in general, yeah. And so I can choose... well, I have only two possibilities. So everything here is labeled by the same thing. They're all group elements. Here I have two possibilities. Either, so remember, I think of Z2 as being 0, 1, and I use addition modulo 2. I have two possibilities. 0 is going to, well, as we anticipate, it's going to correspond to periodic boundary conditions and antiperiodic boundary condition. So here, at first, we have a Hilbert space that is 2 to the n plus 1 dimensional. Right? We have, in principle, in these degrees of freedom, well, we have 2 degrees of freedom there. Now, of course, given the choice you make here, knowing one of these fully constrains the other one, right? So effectively, in that case, it's very easy to see that we have a 2n plus 1 dimensional Hilbert space. Okay, so what we want to do is to write down essentially a unitary mapping where we will always, in such a way that the 1 degree of freedom is always fixed to the same value, and therefore we'll be able to forget about it. So we will be able to get rid of it. This degree of freedom will become classical, and so really we will be working with the 2-dimensional Hilbert space. So this unitary mapping, we saw it actually, well, we saw the same type of operation in the first lecture as this is the way we disentangled the matter and gauge degrees of freedom after doing the gauging. These are the so-called controlled Pauli operators. They act as follows. So all the additions are modulo 2. So let's say if we choose the anti-periodic boundary conditions, so whenever I'm choosing these to be 1 such that G1 has to be equal to Gn plus 1 plus 1, okay, then so this is a 1, sorry. Okay. Then this thing is always going to be equal to 1, right? And so this is what I meant, is that by doing this operation, then we can, regardless of the value of these two, given this constraint, with this unitary, we'll make sure that we will have this degree of freedom K will always have the same value. So we will be able then therefore to discard it. And so very concretely, so on this effective Hilbert space, then what we have is that if I act with this mapping on this term, so if I define the Hamiltonian the way I usually do, I would get a sigma z term between these two operators, and this unit transformation on the effective Hilbert space, it amounts to this operator. And so this is where the -1 comes from. So the -1, just to be clear, when you literally do this operation, you have a sigma, you have an additional sigma z operator that shows up, and then it acts on something that is always 1. So then you pick up always a -1. This is where this -1 comes from.
May I ask a question? Why it's important that G1 equals Gn plus 1 plus 1? It should.
Well, then I chose anti-periodic, right?
Yeah, but the same operator should work for periodic.
No, yeah, it does. It's just in that case you don't get the -1. That's what I'm saying. Yeah. No, what's important is that it's fixed to always the same value whenever it's periodic or anti-periodic. Okay, so this is just to relate to the usual way we think about boundary conditions, but as you can imagine, we cannot typically do that. I mean, here we can do that, or at least in an easy way, because effectively we have a Hilbert space that has the same dimension, whether it's with or without the boundary condition. But as I emphasized earlier, if now you imagine that the degrees of freedom are all labeled by representations of a non-abelian group, then you have really two independent degrees of freedom, and you cannot really use that picture anymore. So this is why we rather adopt the point of view where we modify the Hilbert space rather than just modifying the Hamiltonian. Okay, so let me do now the case. So now let's go through really the classification of the topological sectors. And I'm going to start with an example, which is vec G, so almost the same, but where the group can be arbitrary now. Okay, so the Hilbert space, let me write things, I'm going to write things down a bit more explicitly. Okay, so I have to be careful now with the orientation. So I'm going to make the same choice I've been making quite often, which is that this object X here, I'm just choosing the one which is the simplest scenario, where we just sum over all possible simple objects. Okay, so then we have exactly the same situation as before, where these are just constrained by the value of the degrees of freedom on the. So here I'm choosing the module category to be vec G as well. For now, I'm not making any. I'm not making any more. I'm making the same choice as in the usual picture. And so this Hilbert space, well, at least initially, this is isomorphic to this. Where for now, I don't want to go to this effective Hilbert space picture. Here, I'm really treating these degrees of freedom, even though they are not independent. I'm still treating it as if I had n+1 sites. So the twisted, so the Z here, and so this is an element of the group, right? So the twisted boundary condition here stipulates that the way we are identifying the, well, I'm not strictly speaking identifying them because I'm keeping this Hilbert space with n+1 degrees of freedom, but it puts the constraints that G1 is related to Gn+1 by multiplication by Z. Okay, or I'm just going to rewrite it in this way. Just for future purposes. So now the question is, so that's our boundary condition. Now the question is, what is the symmetry of the model given this boundary condition? It's not something we've really had to deal with so far. These examples, whenever it's abelian, the boundary condition has zero influence on the symmetry. Yeah.
To be confused, I thought you're supposed to have on the bottom, you're supposed to have dual category, right?
Yeah. So here everything is vec G, right? So here I'm using the fact. So it's not something I've emphasized too much, but like the dual of something by itself is always itself, right? Yeah. So far I'm making the canonical choice. So the symmetry operators, which are also labeled just by group elements, they act as follows. So let's say I have a symmetry operator labeled by some group element y. So on my Hilbert space with my n+1 sites, so it takes this state where here I'm using the fact that G1 has to be Z equal to Gn+1. And it acts by also left multiplication by -1. This is just because of the conventions I've been using since the beginning, but it doesn't really matter. Okay. Okay. And so here, this state there, I could just rewrite it in terms of, I could just rewrite this with a new, by just relabeling if you want, where I have a new degree of freedom Gn tilde, Gn+1 tilde, and here G1 tilde. And so now what you notice immediately, if I just check this relation, but now for the tildes, what we have is that the boundary condition is actually modified. Like after acting with the symmetry, if you take sort of the ratio of the group elements associated with side n+1 and 1 is not the same. So we change the symmetry. So generally speaking, this operator uy is going to be a map from one Hilbert space to the other. So here this is the one labeled by Z. -1, 0. Okay. So this tells us one thing, first of all, is that the total Hilbert space, so the one where this boundary condition is a degree of freedom as well, it's something you can just choose, it's going to decompose over conjugacy classes. It's going to decompose into orbits. In the case here, the orbits, the action is by conjugation, so these are just the conjugacy classes. Concretely what it means is like, if you have a boundary conditions in a given conjugacy class, by acting with symmetry operators, you won't be able to leave that conjugacy class. You can go through all the elements in the conjugacy class, but you cannot leave it. So you have a natural decomposition. So the total Hilbert space decomposes over conjugacy classes. Okay, label like this, and the set of conjugacy class, I write it CL of G. So now given a conjugacy class, so Z is the representative of a given conjugacy class, what is the symmetry that is left? Well, or whether so these are not strictly speaking symmetry operators when they modify the boundary conditions. So now we ask, given the boundary conditions, what are really the symmetry operators? So given H with G of Z, so the symmetry operators really that leave the Hilbert space invariance are labeled by objects in the centralizer of the representative of the conjugacy class. I'm going to write it N to avoid confusion, and G of Z. Okay, so this is the set of elements, the set of elements in G that commute with Z. Okay, so indeed, if it commutes with Z, then it's going to leave the Hilbert space invariant. And so what it tells us is that now we have a Hilbert space that has an action by the centralizer of some element, and this Hilbert space then is going to decompose into irreducible representations of this subgroup. So in total, what I've been calling the topological sectors, which is a combination of boundary conditions and, given the boundary conditions, the charge sectors. They are labeled by two things. So a conjugacy class and, I'm going to write it down like this, an irreducible representation of the centralizer. So this is an irrep of the centralizer.
What character did you use?
Here, that's N G.
Is that V? Is that R? Is that
This is a V, just vector space. I mean, the vector space for the corresponding irrep. Or row, I mean, I don't know, maybe I could use row if you prefer. Okay?
May I ask a question?
Yeah.
So last time we discussed symmetries, and they look like we just took our state and we took a line below the state, we pushed it inside, and this was a symmetry.
Yeah.
And now the statement is that if I do the same but with anti...
Yeah, I'm getting there. I'm going to do it graphically now, and yeah.
So it means that for normal boundary conditions, for periodic boundary conditions, I expect still to have just usual symmetry without...
Yeah, so when the periodic boundary condition, generally speaking, is when you choose the identity here. That's what more generally you would call the periodic boundary condition, is when you choose the identity. And maybe just before doing graphically, let me mention that, so given this knowledge, now if you want to build a projector onto a given sector, which we typically need to do when we want to, in order to have the isometry mappings between the sectors, you can, from this information, you can get it by doing some Fourier transform. I mean, there is you will have to do some Fourier transform of your symmetry operators, and you will be able to write down explicitly the projectors.
And here you don't particularly care if the symmetry is invertible or not. For
now, well, I'm using it implicitly in a couple of places, but at the end of the day, no, we won't care. So what I'm going to do is that I'm going to redo this story, basically, like Nigel suggests, kind of graphically, and then this is the way I will treat the general case as well. But the fact that this is invertible, I mean, like in which way, for instance?
No, because sometimes you were also making the case that non-invertible symmetries can be viewed as changing the Hilbert space, one point of view of view them. And if you view them as acting on the same Hilbert space, then they map some part of the Hilbert space to zero.
So these are the case of the non-invertible symmetries that usually maybe come from some self-duality, for instance, because since dualities typically project onto sectors, sometimes if you have a symmetry. But
The ones that you construct using these lines?
yeah, no, I don't. I mean, they could.
I'm not sure.
Some certain combinations of them would, like for instance in RepG. The case we have over here. Well, no, maybe not the backwards. So I have a RepG symmetry, right? If I take indeed a specific superposition of these lines, it's going to amount to a projector onto a given sector. That's possible, but that's not really a problem. I mean, okay, so what is the way we want to rethink this? So I want to do this graphically. So exactly the question is now how do we combine the pictures we had for the symmetry lines, I think from the bottom, in the presence of these defects? Well, what we have to consider are, well, I'm going to draw it like this, are objects that looks like this, where I have my symmetry line here, y, and I have my choice of boundary condition z. So I'm thinking of it as acting from the bottom to the top. So this boundary condition z, by the action of this symmetry line, will be transformed to y minus 1 zy. So here I'm really just using the same graphical calculus we've been using so far. No, sorry, this is a bit of a weird convention. Okay. So here I'm just implementing at every point here, there is a home space, and for the home space, something non-trivial, the fusion rules have to be satisfied, which is just group multiplication. And then it's just a convention of the arrows that give me this specific answer, which is the same we had here. So here you really want to think of interpreting this as, so this is the symmetry line that I need to equip with additional line in order to be able to act on the Hilbert space we have here. And you see that from just by using the multiplication, essentially the fusion rules, the boundary condition is transformed from z to y minus 1 zy. So then the actual action, well, it's really always the same thing. You stack it on top, and then you will just have to use more if moves, but it will always boil down to the same type of rules. So actually, let me do a very similar computation now. Just to clarify, this object and the way you want to think about it, we think of it as an operator, but if you want to think of it in the category what it is a special type of morphisms of the form. So the minus ones are just due to the conventions. Okay. Okay, this is just a morphism like this, right? And there is no choice of basis vector. Okay, so now what I want to do is to consider the operation of stacking two such symmetry operators in the presence of the defects. So the same way we define the composition of the symmetry operators by just putting two next to each other and then sort of stacking them. Now I want to do the same thing, but in the presence of this twist. So it looks, so after stacking them, of course means that the degrees of freedom along which I stack have to be the same. I get a picture that looks like this with the following labels. Here I have 1, minus 1, 0. So I took two of these guys. So really the symmetry operators are labeled by y1 and y2. Then I have an initial boundary condition that is, well, actually z, I don't need to have a label there. And then it first transforms the boundary condition from z to y1 minus 1 z1 1, and then to this one. Now what I can do, so this, remember that we have boundary conditions. I mean, you have to imagine that these things live on the cylinder, right? It's closed at the back. And now I can just, I could do it using my graphical rules, but my graphical rules are all a bit stupid here because the F symbols are all trivial, so I can just simplify immediately. And this whole thing, what it amounts to, it's exactly the same thing as an operator as this thing. I can fuse the two symmetry lines, and then I have just this thing. So this is just the statement that these symmetry operators equipped with this twisting, they form an algebra, the same way the original lines form an algebra. And this algebra is a famous algebra. It's called the quantum double of the group. So usually written D of G. So as an algebra, as a half algebra if you want, or the underlying vector space is isomorphic to these, but it doesn't really matter. But the CG part is really these lines, and the other part takes care of the boundary conditions. So what is important is that this is it's a well-understood object, and the E-reps of this algebra in particular are labeled by exactly what we expect. So by a choice of conjugacy class, and then a choice of representation for the centralizer of the corresponding conjugacy class. So I'm just rephrasing the classification in terms of irreducible representation of some algebraic structure, which is this quantum double.
You get this quantum double if you restrict the solve to like the minimal possible length, because these lines they had a long.
Minimal possible length in the sense. So here.
You had some length. Right?
Yeah. You mean like.
You just take the minimal length.
Like as if there was only one side, you mean, in the chain?
Or like two sides here. Yeah, one side and two.
Indeed. So what happens is that so here indeed it would be like, so if I just look at these pictures, then this is literally the quantum double. Now if you think in terms of like symmetric operators acting on like Hilbert space and so on, then indeed what you get is the dimension of the corresponding sector in the Hilbert space is not going to be directly the dimension of this guy. It's going to be like we are using some kind of Morita equivalence here, where you have a bigger Hilbert space, but then it just. Well, I mean, okay. What we are using here really is that at the end of the day is that we have a Hilbert space that is acted upon by this quantum double algebra. So it has a structure of a module over this double algebra, and therefore it's going to decompose into sectors that are labeled by the E-reps. That's really the statement I'm making here. I'm not making any statement. I mean, I'm not trying to relate the dimension of this object directly to the dimension of Hilbert space. It would coincide indeed in some minimal setting where you had only one side.
Can you clarify what the notation of C to the G means?
Yeah, so these are functions from G to from G to C. So these are two algebras that are dual to each other, and there is kind of some symmetry. The role of the boundary, you see like the role that plays the symmetry and the boundary condition, they are related by sort of the duality between these two guys. And one, I would say, interesting fact, which I won't describe in too much detail, but it's like there is also a well-known equivalence between, so if I look at the representations of the double and another algebraic structure that I wrote down in the first or the second lecture, there was this object that is called the Drinfeld center of vec G, which has the definition has a bit of a different flavor, but you can. It's a way of taking a category, building another category from it, and then you can show that these are equivalent. The reason why I'm highlighting this is because for the more general case, this is the way we will understand the classification of the sectors. Also to illustrate the fact that this is an object that has been studied extensively on its own, and therefore we can rely on many results that are pertaining to this. This is also to relate the classification of the sectors to really the symmetry. Like there is really a recipe, like given the symmetry, there is a construction you can apply to this symmetry, giving you a bigger category, and this will classify the sectors in general. Okay. So I'm going to use now these pictures to do the more general case. I'm going to do it a bit loosely, but I think it will be enough. So more generally, so let's say we have we choose a fusion category C. Then we have a C module category M. So this is really the setup of our generalized ionic picture. And so the symmetry, as I said, I reviewed before, the symmetry is the dual of C with respect to M. Okay. So you have the drawing of the Hilbert space in mind, which is reviewed over there. And so what we want to do is that we're just going to consider the analog of these guys more generally. So how does it look like? Well, I mean, it's pretty much the same thing. Now I'm considering objects of this form. So now I can more generally I can have some multiplicity over there. Also, there is no in contrast to the original case, where I could just deduce the label there, knowing the other ones, and in general, like I wouldn't know. So we have to label everything by different labels. Okay. So we have an object like this, okay, which is, I think of it as a map. So from the Hilbert space, I still with the choice of module category M, labeled by the boundary condition Z1 to the Hilbert space with a different choice of boundary condition. And essentially, I'm going to find the sectors as irreducible representations of whatever is the analog of this quantum double algebra. So how do we do that? Well, the strategy is the same. I'm just taking two of these guys, which I'm stacking. Okay. And here, it may be helpful to give you a slightly different way of drawing these things, which is the following one. Okay. So something like this. So remember that these things, they essentially live on the cylinder, right? What you have is that we have these objects, and we consider close the chain. So I have my symmetry operator is like this, and then I have my defects like that, which I drew backwards, but okay. And so in the plane, it's kind of convenient to project it like this when we want to use the graphical calculus to manipulate it. That's a useful way of drawing it. Okay, so I'm just taking the loop and I'm kind of putting it over it. And since I'm doing it twice, I have two of them, so then I have another one, I'm putting another one like this. So I have my two loops that go over like this. And now I'm just going to use some F moves. So here these are F moves for the dual, for the symmetry, right? Which has the structure of a fusion category. So I can do the same type of manipulations I've been doing in defining the Hamiltonians. And so there are several ways of doing it. The fastest way is to do it like this. So I'm just going to I'm going to use it in order to swap sort of these two lines here, or to pass this one over there. So you get something that looks like that. Okay. Then I'm gonna do it twice now to get something that looks like this. Okay, something like this. So I'm doing it here. I'm doing an F move so that instead of consecutively tensoring with the corresponding objects, I'm first fusing them and then I'm fusing with the result, and I'm doing the same over here. And now I have one of these bubbles that we can pop, right? And so you go back to the original picture. Which is then so the same as what I've been drawing before. Okay. Okay, so as you can imagine, in practice, when you write it down explicitly, you have to be a bit careful because since we bend line like this, you have to make sure to keep track of dual objects and stuff like this. But this is just at the end of the day, this is going to be a linear combination of these guys with some coefficients given by 3 F symbols. So this is actually a fairly it's a fairly well-known construction. So this algebra that we get like this is typically referred to as a tube algebra. So tube algebra. And the reason tube really refers to the fact that naturally they live on cylinders, so the tube really refers to the cylinders. This idea, so the idea of considering algebras built in this way, this is something that goes back to Okneanu back in 1993. And so when I'm saying that this is a fairly well understood construction is in particular because we have an analog of the statement I wrote above, is that it's going to be a theorem. We have an equivalence between the representation of this algebra and the so-called Drinfeld center construction of the symmetry category, which again is just to emphasize that this is a familiar object that has been computed in many cases, and so we are in like familiar territory once we have this. So for many examples, then we know immediately what are the possible sectors because this has been computed before. So this is a bit this is the step that may not be so simple in practice sometimes, but you can do it kind of numerically as well, or at least assisted with a computer. Like you just plug that in, and you can then I should say, I forgot to say, but so these algebras, so first of all, they are finite because there are finitely many diagrams you can write down given a category which is itself finite. It has a star structure as well, and therefore they are semi-simple, and then we can use, since it's a semi-simple algebra, then we can rely on like some well-understood techniques to classify the irreducible representations. You're basically looking for the idempotence. So this thing, essentially the projector, so that when you stack two things, it diagonalizes this product rule, and that's the way we find in practice these simple objects which correspond to the sectors.
And star here is just reversing all the arrows?
Sorry?
To apply star, you just reverse all the arrows?
Morally, yes, but you have to be a bit careful. But at the end, it follows from the fact that the input category already has this pivotal structure, which then we rely on to define a star structure on this. It amounts basically to sort of flipping this upside down, and then to bend everything backwards so that it looks like the original diagram. And this will use the fact that we can dualize objects and everything. Okay, and so before the break, let me just mention yeah.
Sorry, before you erase, So what is the difference between U vec G sub Z and, sorry, not U, H vec G sub Z and H vec G sub something that's conjugate to Z? Because when you're defining the Hilbert space, you're summing over all module elements, right?
Yeah, so these are essentially...
And how do you distinguish between Z and something that's conjugate to Z?
So you should think of the boundary condition as being labeled by the conjugacy class, and then a given representative of the conjugacy class is a boundary state. Sure. But so then there are different Hilbert spaces, strictly speaking, because if you fix the boundary condition to be one specific element in the conjugacy class.
No, but so that's where I'm a bit confused. And so how do you fix the element? Because if you're summing over all G1, G2, dot Gn plus 1, right? Then, so your constraint is that G1 is equals to Z times Gn plus 1.
Yeah.
But,
so then effectively in that case you have one dummy, if you want to sum over them, then there is one of them that is always fixed, right? So it's like having a delta function in your, if you decide to fix this one, for a given, you really want to pick one specific boundary state, then really effectively you have only n many, degrees of freedom on n sides, right?
So then if you want to look at the Hilbert space at a particular topological sector, do you have to take a direct sum over all elements in a conjugacy class?
Indeed, in practice, okay, yes, that's a good point. So in practice, when, so what do we do in practice? So let's say we compute this guy and then we ask what are the simple objects. So simple objects in the case you're talking about the conjugacy classes and all. A simple object in the center there does not necessarily correspond to a simple boundary condition. Indeed, sometimes we have, it's even worse when you have a rep G, when you start from rep G instead. Like really a simple sector is going to be given by a sum of boundary conditions. This can happen. It's because it's exactly in the same way that here the conjugacy class, even though it corresponds to a simple object in this tube category, it's not a simple object of vec G. In vec G, it will be a sum of the simple objects. You sum over the elements of the conjugacy class. Yeah. This is what makes it a bit tricky, actually, in practice. And also, this is what makes it almost non-manageable if you don't really have a super systematic way of doing it. Otherwise, if you try to guess, the sectors that are going to be compatible by just brute forcing, it's almost impossible because sometimes they correspond to indeed like direct sums of boundary conditions. So, yeah. Okay, so the result that is super important, and this is from which everything. This is what makes everything work. So I think it was first formulated by Ostrich and Müger, which says that given two indecomposable, with also all the adjectives that I've been implicitly relying on since the beginning, like the fact that they are finite, symmetrical, and everything. Module categories. So M and N. So we have the following equivalence, and this is why I insisted on translating in this language, because this is the way this result was formulated, is that the center of the corresponding dual categories are equivalent. And therefore, this is also equivalent to just the one where you choose the module to be itself. So this is the statement that the center, the Drinfeld center, is an invariant of Morita equivalence. Okay, so this ensures that the sectors are in one-to-one correspondence, and this is ultimately what we use in order to write down then the corresponding the isometries relating the spectra of compatible sectors. So this is really the most technical aspect of the derivation. So I'm not gonna go into the detail. I would just mention the fact that given so here the equivalent, it's not enough to just know it's equivalent. You have to know in which way this is equivalent. You have to understand really how the sectors, which a given simple object here, a given sector, what does it map to over there? And so given the knowledge of this mapping, so from the knowledge of this guy, then you can construct, we can build so tubes, a different type of tubes. So these are going to be the kind of the duality operators in the presence of these twisted boundary conditions, and so morally they look like this, something that looks like that, where the labels are the following. So this is something in the initial symmetry, so the dual with respect to M. This is something that is going to be for the new symmetry, so the boundary conditions are labeled by different things if you change the symmetry upon dualizing. And this thing is what labels the duality operator, which we saw last time is given by some map between the corresponding module categories. So from the knowledge of this equivalence, you can work out essentially the specific superposition of diagrams of these things that will then map the projector onto a given sector on one side to a projector on the compatible sector on the other side. And these are really the objects that then relate the spectra of the Hamiltonians. And so from this knowledge, with the caveats that in some cases the strictly speaking the dimensions don't match, we have like degeneracies can be different from one side to the other. So up to degeneracies, this is really the fact that this gives us the fact that dual Hamiltonians have the same spectrums. Well, okay, so I know I'm not going into any detail, but it essentially relies a lot on very well understood algebraic statements at the level of this Greenfeld center. Okay, so I think maybe we can take the break now and we will do then an example and talk about some applications in the last part of this lecture. Yeah. Are you good to go? Okay. So let's finish with an example. We're going to revisit a well-known duality, and then I will use this example to motivate some applications of this whole program. So this is the so-called Kennedy-Tasaki duality, which is due, so obviously, it's a result of Kennedy and Tasaki, but also of Oshikawa. Okay, so this is an idea. This is a duality that shed light on the so-called Haldane phase of the Heisenberg model. And so the setup is it's a spin 1 interferomagnetic spin chain. Okay, and the Hamiltonian is the usual Heisenberg model, and I'm working with periodic boundary conditions for now. So these are spin 1 operators. And so this model, when people started studying it, was a bit puzzling because even though it looked like it had a unique ground state, it was not the usual disordered phase, so it was not very clear initially what kind of phase this model was in. And so in particular, so if I'm going to work in the basis, in the SZ basis, so my operators, I'm going to label my states by the eigenvalues of the SZ operator. By looking at the typical configuration of the ground state, so you will end up with something that look like this, for instance. Yeah. It looked like it was, almost like interferomagnetic order. If you sort of forget about the zeros and you just look at the plus and minus ones, apart from some sort of defects, for instance here, you had globally an alternating pattern of plus and minus one, which you would expect for like interferomagnetic phase. And these type of patterns then led two people to come up with like an order parameter to try to identify to be able to tell this phase apart from another one. And this was the first instance, I think, of a sort of string order parameter. So it wasn't a local order parameter; it was a non-local order parameter. So it was given by these people. And this order parameter looked like this. So where alpha can be x, y, or z. Okay, so for some ground state phi, we had something that looks like this. So what I'm writing right now is the bulk part of this string order parameter. So you have two endpoints which are given by this kind of operators you will have for a ferromagnetic phase, and you have in addition a bulk string like this. Okay, so that was essentially the status, and then Kennedy and Tasaki and then Oshikawa revealed that there was some hidden symmetry. At the time it was called a hidden symmetry breaking picture. To be understood that there was a way to actually map this model to write on a duality where the dual model was actually in a ferromagnetic phase. In which case the order parameter would reduce to usual ferromagnetic order parameter. So this order parameter, so it was, I don't actually know how it was found initially, but then so Oshikawa came up with a compact way of writing down this duality operator. So this is the version for kind of open boundary conditions. This is not the one I'm gonna use ultimately, which is not, it's not completely obvious how you generalize this definition at first in the case of closed boundary conditions. So he came up with this definition. Okay. And using this operator and some identities, or you just check first how it acts on the given spin operators, and you can work out the dual Hamiltonian. And this Hamiltonian is the following. So there is a funny term in the middle here. Okay, and this model, so the original model, the Heisenberg model has an SO3 symmetry, and this model has, you can check explicitly, it has a Z2-Z2 symmetry. So it retains the Z2-Z2 symmetry of the original model, and this symmetry is generated by these operators, by these two operators. Okay, you can check explicitly, it follows from There are some basic relations that it is symmetric. And actually, there was evidence that this model was in the Z2Z symmetry was spontaneously symmetry broken, and it was the Z2Z2 in the Z2Z2 ferromagnetic phase. And so more specifically, you can also, and for the given, for the order parameters so the usual order parameters of a Z2Z2 ferromagnetic phase, you could check that the expectation value of the ferromagnetic order parameters for the ground state of this model is mapped to the expectation value of the string order parameter of the original phase. Okay. Okay, I'm skipping a lot of historical background, but main point that this duality was obtained, and it shed light on the Haldane phase by being able to relate it. So many properties of this Haldane phase that were a bit exotic can be explained from the point of view of this dual model.
So we should understand the thing in Hamiltonian being the ferromagnetic.
So yeah, I mean this Hamiltonian is what you obtain by acting with this operator on the original one. Now nowadays we understand much better, of course, what the Haldane phase is, and we understand in particular that the Haldane phase is a so-called Z2Z2 SPT. SPT stands for symmetry protected topological order, or topological phase, rather. And so what are those? Well, there are phases that are symmetric. There is a unique ground state, but the ground state is not a tensor product space. It's not a tensor product. And you cannot map it actually to a tensor product using a constant depth circuit that preserves the symmetry. So this is where the symmetry protected comes from, is that as long as you preserve the symmetry, there is no way to relate the ground state of this phase to the trivial symmetric phase. So using this insight, I want to revisit the Kennedy-Tasaki duality in a way that first of all, we'll make it very easy to deal with closed boundary conditions, which is it's not obvious at first how necessarily you generalize this operator since you have this product here. It's not obvious how you would make it work for closed boundary conditions. And also that will make it easy to address the mapping of the sectors and therefore really solving everything we need for this to be a duality in the closed case. So the first part comes from the fact that what we know about SPTs, so I'm cheating a little bit, we understand that SPTs, given a symmetry G, are classified. So G SPTs are classified by some cohomological data, by some two cocycles. Okay, so somehow we know that this is two cocycles should enter the game at some point. And so specifically here, from the fact that the resulting model has Z2Z2 symmetry, okay, it's going to have to be about a Z2Z2 cocycle.
The model has an larger symmetry, right?
Yeah.
Before you apply duality.
Oh yeah, it has an SO3 symmetry. Yeah, it has SO3 symmetry, but, and I will clarify this afterwards, but it seems that the dual model only retained the Z2Z2 symmetry of the original. But yes, so somehow, in the spirit a bit of what we've been doing so far, we've been dealing with models that sometimes had more symmetries, but we would decide to only focus on, like, you know, for example, we focus on the D6 symmetry of XXZ, right, even though it had a bigger symmetry. So here it has a bit the same spirit. Somehow we are only focusing on the Z2 symmetry of the original model. But yeah, this is important, the fact that there is actually more symmetry.
But are you sure that this dual model has just Z2 times Z2?
No. That's not what I'm saying. What I'm saying is that this is what, after people wrote down this Hamiltonian, they were like, oh, it has a Z2Z2 symmetry. And it was almost magical at first, the fact that it still had a Z2Z2 symmetry. But in the spirit of what we've been saying, clearly this Z2Z2 symmetry, we are missing something, right? Because we start from a much bigger symmetry, so this model should have more symmetry. But for now, I'm essentially treating the Heisenberg model as just a Z2Z2 symmetric model, basically. I'm forgetting about the rest of the SO3 symmetry, which is fine. It just means that it gives me access then to less dualities, essentially.
So could you break the Heisenberg model symmetry to Z2 in some way and still apply the duality and still get something which is Z2 symmetric?
Yeah, I mean, sure, I mean...
It looks like the original model, SO3 symmetry was essential.
No, actually it's not. As far as this very specific duality is concerned, it's not. Yes, you can write down, so I'm not sure exactly how I would break down down to Z2, but I could write down a model that is in the same Z2Z2 SPT phase and that only has the Z2Z2 symmetry. I could do that, yeah. Okay, and so let me just write down, so what we guess will be the relevant cocycle. So for Z2Z2, there is a cocycle, so it's a function of two group elements, and here I'm writing, so I'm going to write elements in Z2Z2 as kind of two Z2 elements, right? And it has the following definition. Okay, so that's what we know for now, and now let's see if we can use what we've learned to recover this duality from this viewpoint. So somehow we want to only focus on the Z2Z2 symmetry for now. And the first task is to rewrite this model using in the anionic chain picture. So this is a case where it's a bit, so far we've only dealt with models where it was fairly easy to write it down in the language. Here it's not obvious in which sense I can encode the spin operators in terms of Z2Z2 group elements. So this is often one of the non-trivial tasks of using this approach, is that if you're given a Hamiltonian, you first have to recast it in the framework. So here the trick is to, so let us rewrite Heisenberg as an anionic chain. Well, yeah, it's going to be a generalized anionic chain. And here the idea comes from the fact that we have to work in a specific basis to have nice spin operators. And this basis will come from the fact that if you look at the restriction of the spin 1 representation of SO3, right, the three-dimensional one, you restrict it to Z2, and it decomposes into three irreps, where same, I'm decomposing the irreps in between two Z2 part. So basically they all show up, but the trivial one. And this, what we're gonna do is that we're gonna, I couldn't explain later if you're interested why we do it like this, but we're gonna use this unitary transformation that performs this decomposition, apply it to the spin operators, to the usual spin operators where the SZ is diagonal, that's the usual basis, and we're gonna to find a new basis of spin operators. And this basis is gonna be very nice. As you will immediately see, basically there will be a lot of zeros, which is what we need in order to rewrite it using in the anionic chain picture with input Z2, Z2. So this is an unconventional basis. What is key here is that in this basis, you never have more than one non-trivial element per row or per column, which is compatible with expressing this in terms of like abelian Klebsch-Gordon coefficients. Like, since we are going to use the fusion rules will all be abelian because it's Z2, Z2, it would be more difficult to encode matrices that don't have this sparse structure. Okay, so these are the preliminaries. So considering I'm going to start from, so vec Z2, Z2. I could also start from rep Z2, Z2, it doesn't really matter. And I'm going to choose the module to be vec, okay? So I have a Hilbert space that looks like this. So there is no non-trivial degrees of freedom horizontally there. and vertically I'm choosing x. So I want a 3-level system, and guided by this observation, I'm going to choose x to be the direct sum of these 3 simple objects. Yeah, so using z2 degrees of freedom, I'm building a spin 1 degrees of freedom by only looking at only 3 group elements and not the 4 of them. Then I'm going to write down the Hamiltonian in this way, and actually the fact that I can write it down like this is already an indication that I'm only looking at the z2 symmetry and not the whole SO3 symmetry. So I'm going to have 3 operators, and they all look kind of similar. I will just write one of them explicitly. So it looks like this. So again, on this I can choose completely arbitrarily how I'm labeling the lines here, and provided that this corresponds to objects in X, and I can put whatever coefficients I want, but I'm actually not putting any non-trivial coefficients for this one. Okay. So this is similar to the way we wrote down the Ising model, for instance. If you remember, we had also like 4 diagrams like this. Okay, so I'm just writing all possible combinations with I'm fixing the horizontal one to be 0, 1. And then I'm just looking at all possible configurations of 1, 0 and 1, 1. The reason I'm doing this is because if you look at this operator over here, if you check that there is these 2 rows and columns are trivial, and the first basis element will be 0, 1. So basically, by doing this is that I'm projecting out these operators, is projecting out degrees of freedom labeled by 0, 1. So this is compatible with these operators, and actually this this thing on this Hilbert space, it acts as x. It acts as these operators SX. And then similarly, I can write down 2 operators in this basis that will give me the SYY and SZZ. So that's just the way we recast the Heisenberg model by focusing on its Z2 symmetry as an annual chain. So here, as we discussed at some point, by formulating it like this, I can only address basically Z2 symmetry. The rest of the symmetry is, I would say, accidental from the point of view of this construction. Now we can discuss later whether we should have considered something else. But, and so the duality I want to consider amounts to replacing VEC, which is the choice of module I've been making so far, by, so I haven't specified this one explicitly before, but this is the one where, so I'm choosing you remember that the module categories over this VEC-G, they were labeled by a subgroup and then some 2 cycle, right? So here the 2 cycle is going to be the 2 cycle we had before. And by choosing the group here to be D2, this category has only a unique simple object, and therefore it's equivalent to VEC. So this is why I'm writing it like this. Very concretely, the module associator, which is the only data we really care about, tells me that if I have, so this, of course, these things act, there is no F symbols here, and it's really just, you see immediately the action, I have nothing to do. Here now there will be some F symbols that are given by this 2 cocycle. And so explicitly, it's just given by this phase, which is the 2 cocycle. Okay, and so now you can just plug that in. So it will introduce some, depending on the specific configurations, you will pick up some -1s, basically. That's the only thing you can get. And you can check explicitly that we recover, so the dual model we get is the action of Kennedy Itasaki, so on which is it's a Hermitian operator actually in that case on the original Hamiltonian. So this is the Heisenberg. Okay, so that's how we recover the Kennedy-Tasaki in this framework. Making very transparent the fact that really this is just about this Tuco cycle. It's just like about inserting this Tuco cycle, which is really what classifies the SPT phases.
Yeah. So here, if we start with input category vec Z2 cross Z2 and model category vec, then the symmetry is the Mortha dual of vec Z2 cross Z2.
Yeah, it's rep Z2 Z2. Yeah, but here it's all abelian though. So here I can just think of it as being rep Z2 Z2, right? Yeah. It's just a choice of basis, really.
So, okay, so you're identifying the contracting dual with the argument.
Yeah. Strictly speaking, it would have been better to start from rep Z2 Z2, but then the module category is slightly more, slightly weirder. I would have to deal with projective representation. So it's a bit easier to present it this way, but it's completely equivalent. Okay, and so now we can keep going. The duality operator. So we've learned that the duality operator is going to be given by some simple object, which is going to be a map between these two module categories. So this is an object in this category of module functors from vec to vec psi. And by going back to the original definition, it's actually this is one of the cases that is fairly easy to do by hand. You can check that this is equivalent to the category of projective representation of Z2 Z2. So this tells us that the duality operator is labeled by a projective representation of Z2 Z2 with the same Tuco cycle, of course. And from that knowledge, we can just apply. I mean, we know exactly how this thing acts, and you can just translate. Just it's simple enough that I can write it down much more explicitly. So the way it acts, so this operator, which I'm going to anticipate, I already write it down like this. It acts as follows. It takes a configuration. Okay, so just be careful. G1 here, I don't mean the first component of G. I mean on the site 1. So it takes a spin configuration like this, and so this operator that is labeled by a projective representation, it acts in a way that is very similar to the way the symmetry operators for rep G act. So it acts diagonally by multiplying the state, something that depends on the projective representation. So you evaluate the projective representation on all the group elements, you take the product, and then you take the trace. And so as you can see, so here the trace is because I'm working with closed boundary condition. If I had open boundary conditions, I would just not take the trace. So here it really makes zero difference to work with closed or open boundary conditions. I mean, it makes a difference, but it's as easy in both cases. And you can also check from this. It's also very easy to check that indeed, if you pull your Hamiltonian through this duality, right? What it will do is that you will essentially shift some group elements. Then you use the defining property of the projective representations. You will pick up some Tuco cycles, and these are the Tuco cycles that will appear in the definition of the Hamiltonian. And one thing we can read off immediately from this as well. So the projective representations are, let me write it down explicitly, it's easy. There is a compact form in terms of the Pauli matrices, the usual Pauli matrices, so the spin 1/2 operators. Okay, it's just given by some product of Pauli matrices in general. And from this you can infer that the trace of asking for the trace to be non-zero, there is only one possibility, which is that G is equal to the identity. That's the only case that is possible. Wait, sorry. No, trace to be non-zero, yeah, because the sigma x operator has a vanishing trace and the sigma z operator has a vanishing trace as well. So the only way to have a non-vanishing trace is for G to be the identity. So this tells us that this whole thing is only non-zero when the product of the group elements is the identity. And this is saying that it only acts non-trivially, or it projects out all the states that are not in the even sector. So dkt projects out, so it is a projector, states not in the even sector. I'm going to say even, because it's like even with respect to both copies of Z2. Okay, so this is, remember for Ising, for instance, the statement we were in the even sector, since you act with, let's say, a sigma Z operator, it's only going to give you a +1 if the product of all the group elements is the identity, right? And you get a -1 otherwise. So this is exactly what this thing encodes in particular. So we do need to address the other sectors in order to be able not to have a mapping that is only restricted to these even sectors. Okay. So this is a fairly simple case. Here, because the topological sectors, it's all abelian, which means that the boundary conditions are not going to constrain the symmetry. It's like you can choose independently, essentially, the boundary conditions and the symmetry operators. So the topological sectors, so there are 16 of them. We have 4 types of boundary conditions. It can be periodic and antiperiodic with respect to each copies of Z2s. Times 4 types of charge sectors. And these are labeled by, as I said, so objects in rep Z2, Z2. So it's the boundary conditions. At the end of the day, we can put these twist operators, but it really just amounts to choosing periodic or antiperiodic in that case. So the duality operators in the presence of these defects, now they look like this. So these are pi. This is my projective representation. There is a unique projective representation, by the way, I should have said. And here we have the boundary conditions are labeled by some objects in. So it's not necessarily completely obvious. Initially, I had, so by construction, a rep Z2, Z2. Well, it acts from here to there. So initially, I had a rep Z2, Z2 object thought as the dual of vec Z2, Z2 with respect to vec. And actually, you can check that if you take the dual with respect to vec psi instead, it does not affect the boundary condition at all. So this is really a simple case in that sense where the boundary conditions are labeled by exactly the same thing. Now this thing, in that case, it's not very, we don't have to think too hard. With like the equivalence of the Greenfield center is fairly immediate. We don't have to take very complicated boundary conditions. It will just follow from what the basis space here. And these are given by the Clebsch-Gordan coefficients. Clebsch-Gordan coefficient, as we mentioned at some point, if you take a linear representation of Z2, Z2, you tensor it, so this is pi as well. You tensor it with the projective representation. It's still projective. It's just there is a non-trivial unitary transformation that do this. This is the data of these Clebsch-Gordan coefficients. You can just work them out explicitly, and then realize that this operator does not map the boundary conditions one-to-one, actually. So what we have is that the charges. Let me write it C. So the charge sector, so here this is a even odd, even odd. This is always preserved. This is always preserved because the operator acts diagonally, this duality operator, so it's not going to modify the charge sector. So this is always mapped to itself, but the boundary condition can change. The boundary conditions can change, and it just follows from the fact that you're taking a trace, and you look at the specific, so you pick some element chi and chi prime. This will amount to picking some, evaluating the projective representation on some group element effectively, and then you look like when is the trace non vanishing, and this will give you some compatibility conditions between chi and chi prime. And what we find is that we have a mapping that looks like this. So if given a charge sector that is non-trivial, the boundary condition is going to be modified as follows. We have a new character which can be expressed in terms of the original one as follows. So it's twisted by the presence of the psi. And actually this formula would be exactly the same one for any abelian group. It would be exactly the same story. Like I could have taken an abelian group and it would have been exactly the same story essentially. So it would depend on the specific psi that we have there. So that's how we work out the mapping of the sectors, and then, so this is a case where that is a bit similar to Kramer's-Vanier in the sense that once we have the mapping of the sectors, it's immediate to have access to the isometry that relate the spectra. Okay, so it's a bit of an overkill to some extent to use this whole machinery for this example, but already it simplifies drastically certain computation. And I should say that this specific mapping was studied recently, so not using this machinery by Lee and Oshikawa and Zheng. So it's actually fairly recent that the actual mapping of sectors was worked out. Okay, so now I want to use the time I have left to talk a bit about, to use this example to motivate something a bit more general. So what we see here is, we saw an example of a Hamiltonian in a given phase, which happened to be in that case a symmetry-protected topological phase, and we were able to map it to a dual Hamiltonian that in that case was symmetry broken, the Z2 symmetry breaking picture. Actually, this is something that you can do all the time. You can always, whenever you have a Hamiltonian, whichever phase it is in, you can always find a dual model where it's going to be in the symmetry broken phase. So this relies on some understanding that we have of phases of matter with some generalized symmetries. So there is, I would say, a theorem which was formalized fairly recently, at least in the language I'm going to use, by Ryan Sandgren and Wang, 19, and let's see. Okay. So the content of this theorem, which relies on a connection between gapped phases and topological field theories, which is clear in 1 + 1 dimension, is that gapped, so 1 + 1D C symmetric phases, so if C can be any fusion category here, are classified by indecomposable C-module categories. So we recover, once again, these module categories. Now, I'm not going to attempt to justify this theorem here, but let's look at, for instance, the usual case when you have an ordinary symmetry, so vec G. We found indecomposable C-module categories. We know what they are classified by, some groups, and also some 2 co-cycles for the given subgroups you can choose. That's the usual, I would say, Landau story, where the symmetry can be broken down to a subgroup in the constant sector. And for whatever symmetry is left, you can be either in the trivially symmetric phase, or you can be in an SPT phase. So that's the example we had here, where the phase would be given. So we had a Z2 symmetry, and we had a non-trivial psi. So this was precisely this vec psi here. That was the module category that labeled the SPT phase. Also, this statement tells us that whenever whenever there is an anomaly, for instance, so let's say again in the case where we have an ordinary symmetry, an anomaly was, so you can think of it as an obstruction to gauge, which mathematically meant an obstruction to having a module category that was equivalent to vec, so a category with a single object. This is a statement that an anomaly, a Tooth anomaly, is also an obstruction to having a trivially gapped phase. You cannot have a symmetric phase. The one that you can always have is the one corresponding to the regular module category, is the symmetry broken phase. You can always have the symmetry broken phase. And so using a bit of an extension of the tools we talked about, we understand when we do a duality, which phase, if we are in a given phase, we understand which phase we go to. So the idea, so relies on the fact that, so mathematically, first of all, we have a theorem that says that the module categories, let's say, for two Morita equivalent categories, are equivalent. This is something that we saw, for instance, in the case where you take vec_g and rep_g, we saw they were labeled by the same thing, a subgroup and a two cocycle. Okay. So this already suggests that, okay, given if you're in a phase on one side, if you have a module category on one side, there is a corresponding module category on the other side. So this is secretly what we're going to use. And very concretely, the way it works is that, let's say you have, so I'm starting from the symmetry, let's say is just C itself, so I'm just taking C over itself, and I'm picking a module category that is P. So this is going to dictate the phase I'm in that case. I think of it as, this is my symmetry now, C directly the symmetry, and I'm in a phase that is labeled by P. Okay. So in the case where it's vec_g, we can really understand in terms of symmetry breaking. When in case it's non-invertible, then we can, by analogy, we have also kind of symmetry breaking and SPT. So we have whatever is the analog for non-invertible symmetries. What happens if I do a duality that amounts to changing, so this is my initial symmetry, to, so this is, sorry, C is the initial choice of module category. Let's say I'm making a different choice. So we already know that now the symmetry is going to be the dual with respect to M. And so this equivalence tells us that there is a corresponding module category. And this corresponding module category is given by this object. So this is the same data that labels, duality operators. In that case, I think of it, this is a category. That is a module category over this via, so the action is via composition of the corresponding map, via composition of the corresponding module functors. Yeah, of course.
So you are reducing, so the first line of this, like above the arrow, right? You said, okay, I have this C module category P, and this labels my phase.
Yeah.
But
actually, I should say the number of simple objects here.
In general, you don't know what your phase is. I mean, you are given a Hamiltonian. How do you know what this P is?
No, of course. I mean, that's I would say a separate question. Like, let's say.
It's a very important question.
Yeah, but then, okay, so this statement comes with also, I mean, at least since then, we understand also, for instance, how to construct the corresponding order parameters associated with all these phases. So you could just, let's say, go through all of them and identify the phase you're in. Or you could also say, yeah, let's say I don't know, but then we have finitely many dualities we can do. Let's do all the dualities and see what we get. I mean, like, it depends exactly what the application of this.
Yeah, exactly. I don't quite understand what is the operational, like, how are we going to apply
yeah.
the machinery?
So here, so first of all, the first bit is that if I'm choosing M to be P itself, so either you know P or then you go through all of them and then one of them will correspond to P.
Suppose you are given a Hamiltonian, how do you know like what is the list of P's, possible P's?
Okay, so then this is supposing that you know the symmetry of the Hamiltonian, at least you identify some symmetry. But that's already I would say it's even even you wouldn't even start thinking necessarily. I mean, it would be hard to even make sense of the phases if you have no idea which symmetry you're in, right?
No, but you started from
symmetry
situation. I mean, because you started from the situation of the Haldane model, and there you didn't do a from scratch calculation. You used this insight of these people who already computed that it's Z2 times Z2. Then you started your machinery. So
well,
you were just given this
yeah. So let me.
And you don't know anything.
So
how do you learn about it?
Okay. So let me just finish that bit, and then I'll try to address this. So the choice we're interested in here is that let's say you know P, or let's say you have a P, or whatever, and then you choose M to be P. Okay. When you choose M to be P, this guy then will be the same as this guy. So this will be the situation where the phase is given by the regular module category. This is the choice you can always make. This is the case you can always choose. This is being in the symmetry broken phase. At least if you, you can be motivated further, but like if we just take this for granted, this is what corresponds to the symmetry broken phase.
When you say symmetry broken, do you really mean symmetry broken, or it means like a possibility of symmetry broken, but you don't know if it's actually broken or not?
No, in that case, I mean really, this is the symmetry broken phase where you have the number of ground states, the number of degenerate ground states is in one-to-one with the simple objects in the module category. So this is really, this is kind of the idea, is that this is a module category. So if you think of the objects as a ground state, you have an action which is going to map the ground state onto each other. This is why the intuition comes from. And so in the same spirit that this is always the phase you can guarantee, we can always guarantee that there is a duality that will take us to the symmetry broken phase. You cannot necessarily guarantee that you will be able to access all possible other phases, but at least you can guarantee that there is a dual model where it's in completely symmetry broken. So let's say we're in the situation for now where we know, for some reasons, we have some arguments, we know in which phase we are, or at least we have a strong suspicion that we are in a given phase. Why would you want to do that? Well, if you're trying to, let's say, simulate the ground state of a symmetric phase, it's typically going to be much easier to be in a symmetry broken phase. You're going to have less entanglement. Like if you're in an ordered phase compared to a disordered phase, you're going to have less amount of entanglement. You're going to need less resources to find a ground state with a given energy. So this is something that is desirable. To go to a dual model where the phase is symmetry broken, you're going to be able to get better simulations there. You can then use these duality operators to apply them to whatever state you found, and it will give you the ground state of the original model. So that's one way we want to use this procedure. Now, you could also use this as a way to identify which phase you're in. Provided you know the symmetry. If you don't know the symmetry, then you can't do much. But let's say you know the symmetry. Then you can go through all the dualities, and you will be able to identify by looking at looking at the result of the simulation. You will be able to identify which phase you're in from there. Based on the ground state that you get, the degeneracy, you will be able to tell, oh, that's the right phase. So in practice, what you probably want to do is indeed you have a symmetry, you go through all the possible dualities. This allows you to say, okay, that's the one. You can identify which phase you're in from that. Because once you can identify the symmetry broken phase, then you can reverse engineer knowing the duality, and you can deduce which phase you were in at the beginning. So that can be a way to identify the phase as well. But provided that you know, then it gives you a computation knowledge to know that. Also, these types of kind of this knowledge of this classification combined with some of the ideas we saw. Another way to apply this is that so once you recast a model in the ionic chain picture, it may allow you to identify symmetries that you didn't know, typically some non-invertible one. We have several examples of models. We saw one like a dual of xxz where we would have just said it has a Z2 symmetry, but actually it has a non-invertible symmetry. And these are typically hard to identify. So we have examples of models that, with respect to an invertible symmetry, are all in the same phase. There is no way to tell them apart. But once you realize they have an additional symmetry, which is non-invertible, in light in particular of this classification scheme, you can tell that they are actually in different phases with respect to this bigger symmetry. So that's another it's one of the kind of application of this type of ideas that people have been considering so far. But yeah, I wanted to highlight in particular this ability to be able to control which phase you end up with, and this can be turned into a very concrete numerical tool actually. So, yeah. And I think that's pretty much everything I wanted to tell you about. So thank you for your attention. If you have further questions, feel free to.
What's the most remarkable application of these ideas so far?
So, well, first of all, I think it's still very much under development. So I think we are at a stage where whether this or whether you think in the continuum or whatever, like in the past few years, it was mainly about establishing the formalism. And it's fairly recently that people are starting to really explore okay, what can we do with that? So I've already mentioned the fact that so first of all, if you can identify, it's always good to identify more symmetries. I mean, this is either because of some for classification purposes or for very practical reasons. If you have more symmetry, if you do in particular numerical simulations, that's always something you want to do. From a computational point of view, for me, the last bit I mentioned is it's one very promising direction actually. This combining these ideas with some tensor network techniques to find ground states, you can really get a computational advantage by being able to go like this to a phase where it's systematically symmetry broken, where you get better accuracy, and then you can reverse, then you can apply the duality to get any ground state you might be interested in. This actually seems to be a powerful idea. So then it's very computational in that case. So generally speaking, you have both, I would say, conceptual and computational results. On the conceptual side, I think it's still being discovered. But yeah, on the computational side, for now, this seems to be the most promising idea. I should also mention, I mentioned at the very beginning, but all these ideas generalize to higher dimensions. Really, we can fairly straightforwardly. Of course, the sum of the mass is not as well under control, but morally, everything generalizes to higher dimensions. Including this last statement, with some caveats, but morally you have similar statements. And this is where it might be even more interesting because, first of all, computationally, it's much harder to simulate, let's say, symmetric phases in higher dimensions, so it might make a drastic difference there. And also, conceptually, I would say that there are higher 2+1 dimensional models and phases are less understood. So this may be where the most remarkable results await.
But what's the language that you use then? Because you are relying quite a lot on this language.
Yeah, so then
but once you start
so then you basically you replace fusion categories by fusion 2 categories, and module categories become module 2 categories, and in that sense, this is kind of the power of this formalism. So even though we using this formalism, we can recover many things that were found in the integrability literature, and for instance, in terms of like representations on temporally libed algebras. I mean, it has a very similar flavor, but it's in a language that, and for physical models, it doesn't generalize to higher dimensions, right? While in this language, it, I would say, readily generalizes to higher dimension. But yeah, it hasn't been pursued yet. I mean, it's really so again, the formalism, some of the formalism has been established, but like concrete applications haven't really been considered seriously yet in higher dimensions. So it's still a fairly young area of research, I'd say.
Thanks a lot.
Thank you for attending.